Alright, welcome back everyone. So in this video, just give me one moment. Okay, we're ready. So once again we have the copper pipe problem. Alright, transporting steam in the copper pipe. But in this problem we have insulation. Yep, we've added some insulation on our pipe, as you can see here. This one, right, this outer layer at R equals R3, we have the insulation. Okay, so give the problem a read for a second and I'll be with you shortly. All right, 1, 2, 3. I hope you have read the problem. So let's see, let's see what's up. The copper pipe needs to be insulated, okay, and the thickness, we've been given the thickness of insulation, R3 minus R2, that's good. Derive the equation for the rate of heat transfer. Okay, that's what we're looking for. We're looking for the equation for the rate of heat transfer. All right. Now you may assume steady state. All right, constant conductivity of the pipe, constant conductivity of insulation. Okay, good. And we've been given the temperature at the inner wall and the temperature at the outer wall. So hopefully that's going to make our analysis a little simpler. So all right, let's start off. Again, this is actually this is a section of the pipe. So at the inner wall we have Tn, the inner temperature, and at the outside wall, at the outside of the insulation, we have the outer temperature. All right, and this can be reformulated in an electrical circuits. This can be reformulated into a circuits problem using the electrical circuits analogy. Okay. All right, so let's just write that down. Good. So using the electrical circuits analogy, we can simplify our analysis. We can really simplify our analysis. So we have the temperatures that we have been specified. Of course, temperature is our driving force, T in minus T out. That's going to be the driving force for heat transfer. And there are two series, the copper pipe and the insulation are thermal resistors, essentially. So let's see if we can expand on that. The resistance of the pipe is going to be the thickness of the pipe. The thickness of pipe is the outer radius minus the inner radius, divided by the conductivity of the pipe, and multiply that by the log mean area of pipe. Okay, we'll talk about log mean area in a second. And next up, the thermal resistance due to the insulation, and that's gonna be the R3 minus R2. That's the thickness. R3 minus R2 is the thickness of the insulation, and you're going to divide that by the conductivity of the insulation and the log mean area associated with the insulation. Okay, we need to talk about log mean areas for a second. So in one of the previous videos, we discussed log mean areas in detail and why we need those in spherical and cylindrical coordinates, because the area normal to heat transfer is varying with radius. So a log mean of pipe is going to become 2 pi L multiplied by R2 minus R1 divided by the natural log of R2 over R1. And the area of the log mean area associated with the insulation is going to become 2 pi L multiplied by R3 minus R2, all of that divided by the natural log of R3 divided by R2. So in the previous video, we derived we derived the expressions for log mean area. Now we're just going to use them. Now we're just applying those, okay? So log mean area, good. Now let's combine all of this. And we know that the overall heat transfer rate is going to be equal to the overall temperature difference, overall delta T, and the total and the summation of all the thermal resistances. In this case, we only have the copper pipe and the insulation, and our overall temperature driving, or our delta T overall, is just going to be the temperature at the inner wall minus the temperature at the outer wall of the insulation. So all of this is good. So I know all of these. All right, I know this, I know RP and RI, and yes, I know each of these. So basically I have each of these parameters, I know. All right, now we've essentially formulated the problem, but if I want to really write down the algebra, it's going to look something like this, which is of course not necessary, but I'm just going to write it here just for the sake of completion. Okay, so the resistance of pipe plus the resistance of insulation, and expand. We know the resistance of the pipe is going to be the thickness of the pipe, R2 minus R1, divided by the conductivity of the pipe, area log mean, P. Ri, the thermal resistance due to the insulation is going to be the thickness of the insulation, R3 minus R2, divided by the conductivity of insulation. Now I'm just now essentially I'm summarizing everything that we've done so far. And of course we need the log mean areas. So log mean area due to P is going to be 2 pi L. We're just summarizing the equations here. R2 minus R1 divided by the natural log of R2 over R1. Good. And area log mean due to the insulation is going to be 2 pi L once again, R3 minus R2. Okay, and here we have it. Hopefully I haven't made any algebraic mistake. The next step is to find out the values of the parameters and just use Excel or MATLAB or whichever software you prefer. All right, so I'll catch you guys in the next part of this video where we actually compute the rate of heat transfer and see how varying our parameters is going to affect our overall rate of heat transfer. So thank you so much for watching, guys, and I'll see you in the next part of this video.